Hi, good morning. I am Jenny Matriz and I will be discussing about types of integer linear optimization models. If all variables are 199 required to be integer, we have an all-integer linear program. The following is a two-variable all-integer linear programming model. If we drop the praise in integer from the last line of this model, we have the familiar two-variable linear program. The linear program that results from dropping the integer requirements is called the linear programming relaxation, or LP relaxation, of the integer linear program. If some, but not necessarily all, variables are required to be integer, we have a mixed integer linear program. For you to understand more, please watch this video.
Welcome! In this tutorial, I'll be answering the following questions for this LP model. I'll also be interpreting the components of LP sensitivity analysis based on this sensitivity report from Excel. First, note here that these objective coefficients here are displayed here in the output. We assume these are unit profits for product A, B, and C, and the constraint right-hand sides are displayed here. So let's begin by examining the top part of the table for optimality ranges. The optimal solution is represented by final values here. A equals 0, B equals 70, and C equals 30. So the optimal objective function value can be found by plugging the optimal solution into the objective function to obtain 5850. Now, these allowable increase and decrease values specify how much the objective coefficients can change before the optimal solution will change. For example, since the allowable increase for A is 7.5, if we increase the objective coefficient of A from 50 to any value up to an upper limit of 57.5, the optimal solution will not change. For the allowable decrease, Excel usually represents very large values with 1e plus 30. So you can think of it as infinity. Thus, the lower limit for the coefficient of A is negative infinity. For B, the upper limit will be infinity, and the lower limit will be 60 minus 5, which gives 55. For C, we have 60 for the upper limit and 40 for the lower limit. So what will happen to the optimal solution if the unit profit on B, that is the coefficient, decreases by 20? We can see here that the allowable decrease on B is 5. Therefore, the optimal solution will change if we decrease it by 20. That is, these final values will no longer be optimal. And what will happen if the unit profit on C decreases to 45 from its current value of 55? You can see here that 45 is between 40 and 60. So the optimal solution will remain optimal, but the total profit now becomes 55.50. Next, what will happen if the unit profit on both A and C are changed to 53? Note that this sensitivity report only accounts for one change at a time. So if there are simultaneous changes, as we have here, we have to check if the sum of the ratio of proposed changes to allowable changes is within 100%. If the sum of this ratio is over 100%, the optimal solution may no longer be valid. This is called the 100% rule. The proposed increase in A is 53 minus 50, which is 3, and the allowable is 7.5, giving a ratio of 0.4. Whereas for C, the proposed decrease is 55 minus 53, which gives 2, with an allowable decrease of 15, giving a ratio of 0.133. The sum of these ratios is 53.3%, which is less than 100%. So the optimal solution will remain optimal, and the total profit becomes 57.90. Now let's discuss the reduced cost for A. The reduced cost of negative 7.5 here represents the amount by which profit will be reduced if we include a unit of A in the solution. In essence, product A is not attracting enough profit to warrant its inclusion in the product mix. To include product A, or to make it positive, its profit contribution needs to improve by at least 7.5. But at its current value of 50, making A positive in the optimal solution will bring a reduction of 7.5 to profit per unit. Now, the bottom part of the table titled Constraints addresses the range of feasibility. That is the range for the right-hand side of a constraint where the shadow price remains unchanged. For example, as long as the right-hand side of constraint 1 is between 93.33 and 110, the shadow price of 60 will apply. Shadow price here refers to the amount of change in the optimal objective function value per unit increase in the right-hand side of a constraint. So what will happen to optimal profit if the right-hand side of constraint 1 increases by 5? Notice here that the allowable increase for constraint 1 is 10, so an increase of 5 is allowable. Therefore, the optimal profit will change by 5, the amount of change, times 60, the shadow price, to give 300. Since this is positive, profit will increase by 300 from 58.50 to become 61.50. And what will happen if the right-hand side of constraint 2 decreases to 250? Notice here that the allowable decrease for constraint 2 is 30. The current value is 300, so decreasing it to 250 is a proposed decrease of 50. Since the proposed decrease exceeds the allowable decrease, the shadow price is no longer valid. As a result, we cannot tell what will happen to profit based on this output. We need to resolve the model. Next, how will the objective function change if the right-hand side of constraint 4 changes to 44? The current right-hand side value for constraint 4 is 60. Changing it to 44 represents a decrease of 16 units, which is less than the allowable decrease of 60. Therefore, the shadow price applies and the total profit changes by negative 16 times negative 2.5 to give 40. Since this value is positive, optimal profit will actually increase by 40 to become 58.90. For slack and surplus values, we simply take the difference between the final value, that is the left side of the constraint, and the right-hand sides. Constraints 1 and 2 are less or equal constraints, so they will be associated with slack variables, while 3 and 4 are greater or equal constraints and will be associated with surplus variables. So the slack value for constraint 1 is 0, and for constraint 2 it is 30. The surplus for constraint 3 is 20, and for constraint 4 it is 0. Lastly, the binding constraints are the ones that have final values equal to the right-hand sides, that is, the ones with 0 slack or surplus values. So constraints 1 and 4 are binding, while 2 and 3 are non-binding. Note also that the binding constraints have non-zero shadow prices. And that's it for this video. Thanks for watching.
Good day everyone, I'm Caliwag and I will be discussing an example of integer optimization, which is the Eastbourne Realty. First, let's define our decision variables. We're going to use to represent the number of townhouses as the letter T, and we're going to use to represent the number of apartment buildings as letter A. Now that we know what our decision variables are, we can put together our objective function, and that is to maximize 10T plus 15A. We have three constraints that must be satisfied. First, we have to look at 282T plus 400A, and it has to be less than or equal to 2,000. You may be looking at that and say, well, where did that come from? Basically, we're saying that the price for the townhouses is 282,000 plus the price of the apartment building, which is 400,000. Both of those together, depending on the number that we produce, has to be less than or equal to 2 million. Those numbers are represented in thousands. Now that we have the manager's time constraint that we have to put in there, let's represent 40 plus 40A, and it has to be less than or equal to 140. So we only has 140 hours to provide maintenance for these buildings. To provide maintenance for these buildings, the townhomes takes 4 hours and the apartment building takes 40. So those together, depending on the amount that you produce, has to be less than his available time of 140. The last constraint is related to the availability of townhomes. So T has to be less than or equal to 5 because there are 5 townhomes available. The variables T and A must be non-negative. We can't buy -1 townhomes or -1 apartment buildings because that won't work. And in addition, the purchase of the fractional number of townhomes or a fractional number of apartment buildings is unacceptable. And that's the nuance that we have to address now. Now that we have the model for the problem, we realize that this is what we called a linear all-integer program. Each townhome has to be a whole unit. Each apartment building has to be a whole. If you look at this figure, you will see that each of the constraints plotted on the chart we talked about earlier is the idea of feasibility region. So you start to see that the feasible region, where each of the solution in that region will solve the constraint, remember that our objective is to maximize the amount of properties we can buy based on the budget that we have. However, this problem is different because we have to choose integers and we have to choose whole numbers as you see there. The objective function now has not only passed through the feasibility region or the feasible region as we call it. It also has to strike one of the whole integer numbers of apartment buildings and townhomes. The optimal integer solution, as we can see here, is where T is equal to 4 and A is equal to 2. The objective function now is equal to 70. That line, as you see on the graph, goes through the point of T equals 4 and A equals 2. We can't go beyond that point because we have no amount of apartment buildings and no amount of townhomes in whole numbers. And that will solve the objective. So point B, the intersection of the manager's time constraint and available funds constraint, that is where T equals 2.4 and A is equals to 3.252. We know that won't work, even though that's the optimal solution based on the feasible region. So why does it won't work? Because we need integers. We can sell or buy 2.479 townhomes and we can sell or buy 3.252 apartment buildings because it has to be whole number. Now, If we could do that, then the optimal cash flow would be 73,574. In many cases, a non-integer solution can be rounded to obtain an acceptable integer solution. As we learn around numbers when we're in middle school, elementary school, even when in high school. We did math and we always rounded those numbers up. However, as we learn when we're doing regression analysis, you're making an estimate of a number versus its actual number. There's error involved in this case because we're doing integer linear programming, and the error that will be involved by rounding up or down could make sure that you don't have the optimal solution. So with that, there's something that we're going to do. The optimal solution, if we relax all of the constraints as it relates to integer linear programming, will be townhomes equals to 2.479 and apartment buildings equals to 3.252. So if we rounded it, we expected to have substantial economic impact. Suppose we round the solution using this process and use 2 townhomes and we use 3 apartment buildings. We put that into our objective function. We have 10 times 2 plus 15 times 3 is equals to 65. The annual cash flow of $65 is substantially less than the annual cash flow of $73,574 provided by the solution to the LP relaxation. Rounding to an integer solution is a trial and error approach. Each rounded solution must be evaluated for feasibility, as well as for its impact on the value of the objective function. Even when a rounded solution is feasible, there is no guarantee that the optimal integer solution has been found.
Hello, great day everyone. I am Nathaniel Romeo and I will be discussing solving integer optimization problems with Excel Solver. When a solver model includes integer, binary, or all different constraints, it is called an integer programming problem. The worksheet formulation and solution for integer linear programs is similar to that for linear programming problems. Actually, the worksheet formulation is exactly the same, but some additional information must be provided when setting up the solver parameters and options dialog boxes. Constraints must be added in the solver parameters dialog box to identify the integer variables. In addition, the value for tolerance in the integer options dialog box may need to be adjusted to obtain a solution. Let us demonstrate the Excel solution with this video.
In this video, we're gonna solve the knapsack problem, which is the integer linear optimization problem using Excel. So what we said in the previous video is that this problem has an additional constraint, and this constraint is because the variables or the decision variables of this problem, they should be integers, and this is because of this statement: each investment must be made in full if it is made at all. And then in the previous video, we did the mathematical formulation, and then we're gonna solve our problem. Now guys, what I did, I copied this table to Excel, and then I remove 1, 2, 3, 4 because these should be my decision variables. So here guys, you can try any numbers whenever you click on data and then solver. The Excel will change these values so that you reach the optimized solution. And then I added the capacity, which is here 14, because they said that the investment bank has a total budget of 14 million euros. And I add this cell here for the profit, which means for my objective function, which is also in this case a maximum. So guys, I'm gonna sort by this profit or by this objective function, and as I said here, it is the maximum of the 16 times x1 plus 22 times x2 plus 12 times x3 plus 8 times x4. 4. All right, so if I'm gonna do it explicitly, it is like this. Don't forget to put that equal sign whenever you wanna add an equation to any Excel cell. All right, so it is equal to x1 times 16 plus x2 times 22. You can follow me here, all right? Plus x3 times 12 plus x4 times 8, all right? So this is the profit basically. Now, of course, it is 0 because I didn't put any number here. Let's say I'm gonna put this 1, 2, 0, 4. So of course you will have a short-term profit, and Excel will change these values whenever I click on solve. Now, guys, I'm gonna teach you another way, simple way to do this equation, and it is called the sum product. So I can say equal. Okay, sum product means I'm gonna sum the product between these cells. So sum product of what? You have to open your parentheses and you have to specify here 2 arrays or 2 matrices. All right, so the first array here is these values, the decision variables, and then I'm gonna say comma, and the second array is the revenue, and then I'm gonna close my parentheses. So in this case, guys, what Excel will do is to take the first cell of this array, multiply it by the first cell of the second array, plus the second cell times the cell plus the cell times the cell plus the cell times the cell. And then if I click enter, you can see, guys, that you will have the same value. So if you do it explicitly, this will waste time. Now, if you use some product, you can have directly also the correct answer. Okay. Now for the capacity, I can also use sum product. So I'm gonna use it. Sum product between what and what? Between basically this one, the number, the decision variables, and this amount. Then of course this should be less than 14. All right, this should be less than the maximum capacity. Now it is not less than this because in fact I'm using some random numbers. So I put this 1, let's say, and then I put this 2. I still exceeding the capacity, so let's make this 0. So here I am near the total capacity, but I'm not sure if this is the optimized solution. So let's click on solve in order to know if this is my optimized solution or in order to change all these decision variables. So I'm gonna click on data here. Guys, if you don't have this solver, try to go back to the previous videos to add it, all right? And then click on solver. Now, what is my maximized function here? Basically, it is the profit. So this is my maximized function, or this one, all right? So you can choose between them. They are the same, okay? And I need to maximize it, of course, because this is a profit problem by changing which variables. These my variables to be changed, subjected to what constraint. In fact, the first constraint is that this capacity here should be less or equal to the maximum capacity, and then I'm gonna add the integer constraint. So what is my integer constraint? This should be integer. So you have to click on this arrow and you have to choose this integer and add this should be also integer. Add this should be also integer. Add, and this one should be also integer. All right, so I'm gonna click on OK, and then make sure you are seeing all your constraints here. Then click on simple linear optimization simplex. It is the simplex method, and then you have to click on solve, and then you can keep the solver solution. And then as you can see, guys, you have to invest only in the first type of investment and on the third type of investment. And make sure, guys, that the first type has two investments. Each one has an amount of 5 million euros, and the third type has only one investment of 4 million euros. And as you can see, guys, the capacity reaches its maximum. So I can benefit from the total amount of the capacity of this bond in order to make the maximized profit, which is here 44 million euros. So that's it. This is the integer linear optimization problems.
Sensitivity analysis often is more crucial for integer linear programming problems than for linear programming problems. A small change in one of the coefficients in the constraints can cause a relatively large change in the value of the optimal solution. To further understand it, kindly watch this video.
An example of sensitivity analysis. Let's start off with the base case on the left. The projected income statement of a company has $1 million of revenue, minus $600,000 of variable costs, which leads to $400,000 of contribution margin. After deducting fixed cost of $200,000, operating margin is $200,000. What is the effect of a change in revenue, more specifically a drop of 10%, on operating margin? Wrong question. Not every type of change in revenue has the same effect on operating margin. Currently, the company expects to sell 100,000 units of one single type of product at $10 each. If we want to analyze the impact of a change in revenue, input variable, on operating margin, target variable, then we should either take a 10% decrease in volume or a 10% decrease in price. Or even better, analyze the effect of each of these versus the base case side by side. A 10% decrease in volume leads to revenue of $900,000. 90,000 units sold at $10 each. A 10% decrease in price also leads to revenue of $900,000, but with a different composition. 100,000 units sold at $9 each. So far, so good, so what? That question is answered in the next line of the projected income statement. Variable costs in the case of a 10% drop in volume are $540,000. 90,000 units that cost $6 per unit to make. In other words, 90,000 units in revenue and 90,000 units in variable costs. If there is a drop in volume, then both revenue and variable costs drop by 10%. Variable costs in the case of a 10% drop in price stay at $600,000. 100,000 units at the cost of $6 per unit to make. Revenue drops, but variable costs stay the same. As a result, the contribution margin in the volume drop scenario is $360,000, 90,000 units times $4 per unit, while in the price drop scenario, it is only $300,000, 100,000 units times $3 per unit. Deduct the fixed costs, which stay at $200,000, the same as in the base case scenario. Then look at operating margin. $160,000 in the 10% volume drop scenario, but only $100,000 in the 10% price drop scenario. From this, we learned that we can expect a 10% drop in volume to lead to a 20% drop in operating margin, while a 10% drop in price would lead to a 50% drop in operating margin. Be much more afraid of a drop in price than of a drop in volume. What we have done so far is called a one assumption at a time scenario analysis, analyzing the effect of varying one model input factor at a time while keeping all other fixed. In real life, many assumptions may be linked and move at the same time, in the same direction or in opposite directions. What if both volume and price drop by 10% at the same time? Our new revenue would be $810,000, 90,000 units at $9 per unit. Variable costs, $540,000, 90,000 units at $6 per unit. Contribution margin, $270,000, 90,000 units at $3 per unit. Fixed costs, $200,000. Operating margin, $70,000. What we learn from this is that a 10% drop in volume and a 10% drop in price at the same time lead to an expected 65% drop in operating margin versus the base case.
Our next topic is about applications involving binary variables. In many applications, binary variables provide selections or choices with the value of the variable equal to 1 if a corresponding activity is undertaken, and equal to 0 if the corresponding activity is not undertaken. The capital budgeting, fixed costs, distribution system design, bank location, and product design or market share applications presented in this section make use of binary variables. For capital budgeting, as seen in the table for ice cold refrigerator company, let us define 4 binary decision variables. P is equal to 1 if the plant expansion project is accepted, and 0 if rejected. W is 1 if the warehouse expansion project is accepted, and 0 if rejected, as well as M is equal to 1 if the new machinery project is accepted, and 0 if rejected. R is equal to 1 if the new product research project is accepted, and 0 if rejected. In a capital budgeting problem, the company's objective function is to maximize the net present value of the capital budgeting projects. This problem has 4 constraints, one for the funds available in each of the next 4 years. A binary integer linear programming model with dollars in thousands is. Second one is fixed costs. In many applications, the cost of production has 2 components, a setup cost, which is a fixed cost, and a variable cost, which is directly related to the production quantity. The use of binary variables makes including the setup costs possible in a model for production application. Here are some examples from the module. And third one is bank location. The bank may locate branches in a country if the country contains a PPB or is adjacent to another country with the PPB. Thus, the linear program will need one constraint for each country. For example, the constraint for Ashtabula country is x plus 1 plus x plus 2 plus x12 plus x16 is greater or equal than 1, as seen on the map. Note that satisfaction of this constraint ensures that PPB will be placed in Ashtabula country or in one or more of the adjacent countries. This constraint thus guarantees that Ohio Trust will be able to place branch banks in Ashtabula country. And the last application is the product design and market share optimization. Conjoint analysis is a market research technique that can be used to learn how prospective buyers of a product value the product attributes. In this section, we will show how the result of conjoint analysis can be used in an integer programming model of a product, design and market share optimization problem. In a typical conjoint analysis, a sample of consumers is asked to express their preference for a product with the chosen levels for the attributes. Then regression analysis is used to determine the part worth for each of the attribute levels. In essence, the part worth is the utility value that a consumer attaches to each level of each attribute. Provided part worths from regression analysis, we will show how they can be used to determine the overall value a consumer attaches to a particular product. Here is the video.
Welcome! In this tutorial, I'll formulate linear integer programming models involving binary or 0-1 variables. Binary variables are employed when there is a yes or no situation. That is to indicate whether a selection is made or not. For example, suppose we have 4 different projects to consider. We can either select a project or not select it. So for the first project, we can define the decision variables as follows. x1 equals 1 if project 1 is selected and 0 if not selected. We do the same for projects 2, 3, and 4 by defining x2, x3, and x4. Or we can simply write xi equals 1 if project I is selected and 0 if not selected, where I equals 1, 2, 3, and 4. Now suppose each project has a lifespan of 3 months, January to March, with corresponding outlays or costs in thousands of dollars shown here. Suppose these are the funds available for selected projects each month, and these are the net returns in thousands of dollars from each project. In this case, our objective is to maximize return, which is 217x1 plus 125x2 plus 88x3 plus 109x4. Since project outlays are constrained by available funds, we write for January 58x1 plus 44x2 plus 26x3 plus 23x4 less than or equal to 120. We do the same for February and for March, and then complete the model by stating that the decision variables must be binary. Upon solving this model using software like Lindo or Excel Solver, we find that the optimal solution is x1 equals 1, x2 equals 0, x3 equals 1, and x4 equals 1, with a corresponding net return of 414. That is, to maximize net return, undertake projects 1, 3, and 4 only. Let's now model a fixed cost problem. Suppose a small company receives an order to supply 1,000 units of a product. The company has 3 machines that can be used to produce the product. Here are the variable costs per unit produced from each machine, here are the fixed costs, and here are the machine's capacities. Our objective is to minimize total costs. We're going to need 2 types of decision variables in this case. One set for the number of units produced from each machine, and because of the fixed costs, another to indicate whether a machine is being used or not. So for the units produced, we write xi equals number of units produced on machine I. That is, x1 represents the units produced on machine 1, x2 for machine 2, and x3 for machine 3. Now, because fixed costs indicate that the entire cost will be incurred if the corresponding machine is used to produce it all, we define another set of decision variables. For machine 1, we can write y1 equals 1 if machine 1 is used, 0 otherwise. That is, if x1 is greater than 0, y1 equals 1. Otherwise, y1 equals 0. For all 3 machines, we write y1 equals 1 if machine I is used, 0 otherwise. So for the objective function, which is to minimize total costs, we write minimize 2.39x1 plus 1.99x2 plus 2.99x3 plus 300y1 plus 250y2 plus 400y3. That is, we multiply variable costs by unit produced and multiply fixed costs by the corresponding 0, 1 variables. When y equals 1 here, for example, it means that machine 1 is used and the fixed cost of 300 will be incurred. And when y1 equals 0, machine 1 is not used, so the fixed cost of 300 will not be incurred. For the constraints, we have an order here to supply 1,000 units. So we write x1 plus x2 plus x3 equals 1,000. Equality is used here because we have to meet the order or demand placed by the customer. Now for the capacities, normally we just write x1 less than or equal to 400, x2 less than or equal to 550, and x3 less than or equal to 600. Note that this x1 less than or equal to 400 constraint simply states that we can produce up to 400 units on machine 1. But if the machine is not used at all, this won't be possible. So whenever we have fixed costs associated with minimum requirements or maximum capacities, we usually multiply the capacity by the corresponding binary variable. So the correct format is x1 less than or equal to 400y1. That is, when y1 equals 1, We can produce up to 400 on machine 1, and when y1 equals 0, 0 units should be produced. We do the same for machine 2 and machine 3. We can then move the variables to the left side of the constraints and state that the xi should be non-negative and the yi is binary. On solving this model, we obtain x1 equals 0, x2 equals 550, x3 equals 450. And for the binary variables, y1 equals 0, y2 equals 1, and y3 equals 1, showing that only machines 2 and 3 should be used. And that completes this fixed cost problem. In the next video, I'll be showing how to formulate some relational constraints using binary variables, including multiple choice, mutually exclusive, co-requisite, and conditional constraints. Thanks for watching.
And now for modeling flexibility provided by binary variables, let's watch this video.
Continuing on management decision tools discussion on integer and binary programming model. So here's a slide that is really nice because it summarizes a few tricks that we frequently use on models that contain binary variables. So for instance, oftentimes we'll be constraining the model to say that we need to pick k choices out of n possibilities. It can be as described here, choosing k projects out of n projects to take part in, to invest, to participate in, and so on and so forth, right? To work something out and then ignore the rest of the n minus k projects. So how can we describe that constraint? And that's easy, right? So if we have x1, x2, x3 to xn reflecting yes or no, taking part or not taking part in project I, then we just need to add up all the binary variables to be less than equal to k. So example, suppose n is 10 and k is 3, then well, 10 is too many, maybe 5 and k is 3, then what we are writing on the summation symbol here is just x1 plus x2 plus x3 plus x4 plus x5 is less than equal to 3. That will be reflecting the desire to constrain it to at most choose at most 3 projects out of 5. Does it make sense? Yeah. What if we need at least? All right, so using the same example, if we are to choose at least 3 projects out of 5, so it could be 3, 4, or 5. Yes, you get it. It's basically just turning the sign. So you see that it's very important to write the sign carefully. So this is at most, right? And this is at least. Just tweak of a symbol changes the constraint, the meaning, and the solution immediately. So it's very consequential. Okay, what if we need to have exactness? What if we have situations where we say, you know what, we actually need to choose exactly 3 extracurricular activities to participate in out of 20, 3 at the most, because I have time for 3. We're encouraged to do 4, but I only have time for 3, so 3 is the most. Which 3? So if that's the case, then yes, you get the idea. We can modify from here and say that, well, it will be exactly equal to 3. Exactly k projects out of n choices to choose from. Yeah, okay, so it's very easy if we have gone through this discussion. And once you think about this this example and try out on some other exercises, after a few times you get a hang of it. Once you hear the words, you know, like I want at most 5 settings out of all possible 20 combinations. I want at most 4 different flavors on my ice cream, although I know you have 15 different flavors. You know, so all these are beginning to trigger the sense that, oh yeah, I think I need to write it in this form. Okay, all right. So next is project J, that means xj, is conditional upon project I. And this is rather impactful. In other words, you choose project J, all right, you may or may not choose project J, depending on whether you choose project I. So I like to think about it as project I is dominant. That means if project I is not chosen, project J is definitely not chosen. But if project I is chosen, all right, then think about project J, because project J may or may not be chosen. So let's take a look at this. If xi equals to 0, then that means xj is less than or equal to 0. And remember that because xj is also non-negative, this implies that xj has to be 0. Yeah, okay, so that's correct. If we are not doing xi, then definitely don't think about xj. But if we are doing xi because solver somehow sets it to 1, then solver must consider xj, because now xj is less than or equal to 1, and being binary means that we may or may not choose xj. So xj equals to 0 or 1. That's good, right? So give you an example to think about how this may relate to real life applications. I'll give you a very simple but nevertheless pretty common sense example, and that is building a factory and building a warehouse. Okay, so I just write in short, as I don't have a lot of space here, but please write something more meaningful. So xi is a binary variable. It's if it's 1, it means we should build a factory, and 0 otherwise. xj is that we will use additional funding, right, to build a warehouse. We'll build a warehouse, all right, but this warehouse is not for running a third-party business. It's to store the products, manufactured products for our factory. Now, obviously, if we don't build our factory, then we shouldn't be building this warehouse because it's not storing anything. Nothing is being produced. But if we should build a factory, then we have to think about the site. Can it contain a decent factory? Can the factory will the factory be too tall to exceed the building constraints, building limits, control limits? Do we have enough money, and so on and so forth, right? Do we have enough roads, and so on? So we may consider building a warehouse, or we cannot because of other reasons, not because we build a factory. So in this case, we want to tie the connection between the two, all right? And the way to express it is building a factory is a main thing to consider. It's the dominant decision variable. So something has to be less than or equal to the dominant decision variable, and that something is the decision to build a warehouse, and which is exactly taking this form. So the next time you encounter a situation like this, build a factory or build a warehouse for use by the factory, then you can think about this. So another quick example would be building a condominium. Should we consider building a garden? All right. So if finally we're not building a condominium project, then don't even have the garden, because the garden is to serve residents for the condominium. But if we build a condominium, do we want to build a tall condominium, maybe at the expense of having a garden, or a lower condominium, but we have more resources, more capital, and so on and so forth to build a very, very nice landscape garden, right? So the decision to build condominium, major one, the dominant one. So X garden less than or equal to X condominium. Yeah. All right. So once we get a hang of it, we find that it's very expressive. It allows us to talk about if this, then that. If this condition is true, then that. Almost like programming the model without actually writing a program, because it is not a sequential running of the constraints within solver, right? It's all carried out in simultaneous consideration. Good. Let's move on to co-requisite. So a decision of do project xi is co-requisite with decision to do project xj. if you do J, then you do I. If you do I, then you do J. If you do not do I, then you don't do J, and so on. Yeah, so that means they are the same decisions. And what that means is that xj is 1, xi is 1, and if xj is 0, xi is 0. Now, of course, the question is, why don't we just, delete one of the variable and just say that xi is a decision for doing project I and j. That if it's 1, then do both I and j. If it's 0, then don't do either one. And that understanding is correct, but maybe not always that extreme in some cases. That is to say that while the logic is correct, sometimes we do need two variables that need to be linked, connected, in the sense of putting them on the left and right side of the equal sign, such as this, right? The reason is that sometimes we think about having two departments, right? The output of department A, right, has to be flowing at the same rate as the ability for department B to take in the inputs and then continue the processing, right? So you want the rate of output and rate of input to match. So if the decision variables of XA refers to the output rate, B refers to the input rate, they need to be forced, equated with each other, so that when we obtain the optimal solution, things will work out right. Instead of XA outputting a lot faster, a lot more than what department B can absorb, then there'll be problem. So in that case, even though we describe output A and we describe output B, input of B, we want them to be kept separate, and then having such a equal sign to force them to be having the same value, so that it is more expressive, that output A is output A, input of B is input of B. Yeah, and then having the equality sign expresses our knowledgeable expression. We did include this consideration that the output of A needs to be the same as input of B. So in those situations and many more, right, such as factory A output and the rate of processing ability, the capacity of factory B taking outputs from factory A, and so on and so forth, right? So many a times when A develops the model constraints, B develops the models and constraints, sometimes separately, sometimes over different timings or by different peoples, and then we need to integrate them. And then there is a need to, your output needs to be the same as your input, connect them together like this. Okay. And finally, we have this also rather expressive case where projects I and J are mutually exclusive. So what does that mean? It means that when you do project I and J, right? So mutual exclusivity means that xi and xj are not allowed to be one simultaneously. That's all, right? So xi and xj can be 0, 0, okay, no problem. Do I, don't do j, that's okay. Do j, don't do I, that's okay. Do I and j together? No, that's not okay. All right. Now that's easy to try to talk about it in zeros and ones, but can we think of a useful situation? So again, I've given you the build factory, build warehouse, right? So I want to give you another simple situation, simple story to remember. Suppose the developer acquired a land, right? And the land is licensed, is permitted to be built with condominium or factory, right? So X condominium, build condominium. All right, and X factory, build factory. So we ask, shall we build condominium or build factory? Building condominium, there may be a lot of profit. Building factory, we can sell it off fast and then therefore deploy our workers to build other factories or other projects. What should we do? What should we do, right? So we want to, amongst other things like budgets and workers and everything, we want to express the fact that, you know what, we only have one piece of land. You cannot build both condominium and factory, even if you have money and factory and time and the license, right? So we want to say that the decision to build condominium and factory, they are mutually exclusive. All right, so you cannot have ones for both the decision variables. If XC and XF, they are either one is one, then which will mean that we build condominium, don't build factory, or that's okay, or we don't build condominium, build factory, which is okay. Is it okay if we don't do either one? We don't build condominium, don't build factory. In this case, answer is yes. Uh, or rather, the optimal solution might be to just leave it because maybe it's too costly to develop it when the project is not selling well in this climate. Maybe the COVID-19 climate, it's not selling well. So better don't build. Who knows, right? So it is permitted to not do anything. Both are zero, but it is not permitted to have both. That will be what we call mutual exclusivity.
Hello, I am Nerveza and I will be discussing generating alternatives in binary optimization. The use of binary in linear programming problems are common. Problems that need to find the optimal solution are perfect for this kind of solutions. In binary problems, each variable can only take on a value of 0 or 1. This may represent the selection or rejection of an option, turning on or off, yes or no, or many other situations. To understand more, we will have a simple problem. Rachel wants to spend her summer selling sweets in order to buy herself a new bike. She wanted to sell gummy bears, bubble gum, sour bells, and cookies. However, she has only limited funds for every month, so she would have to give up selling something in order to fit her budget. As we can see on the table, Rachel only has 120 pesos for April and 80 pesos for May, and her calculated funds needed exceeded her budget. In order to know what product is needed to remove to get the maximum profit that fits our budget, we need to solve this through the use of binary options using Excel Solver. To solve Rachel's problem, we will use Excel Solver. So first we need to associate all the variables or the constraints to a binary number. 1 meaning it is included, 0 means it's not. For this we will use the Excel's sum product function. To solve the total funds needed, we will add all of this and associate it with the binary numbers. As you can see, when we change this 1 into 0, 23 will be removed through the equation, means it's not included, and when 1, it will be included again. So using Excel Solver, our objective is to have the maximum profit. So our changing variables are the binary numbers, and we will add our references with this. And we will turn these numbers into binary constraints. So we have our parameters, and we will just click solve. So in our solution, the gummy bears are the ones that needed to be removed in order to have maximum profit of 212 pesos. By removing the gummy bears, we are able to reach our budget while still having the best possible returns. Our maximum profit that can be achieved with our limited money is 212 pesos. That is all for today. Thank you for listening.